Good evening, Dr. Sunil.
Hi, good evening.
This is my. I thought I'll address this issue this time.
Which one? Oh, right. Okay. No, yeah, you're talking about the Botox talk.
No, I am giving application of artificial intelligence in prognostication.
This one. This one. You know, we had a small glimpse of it during the stroke subsection.
Yeah, I thought it requires more explanation than a talk there. So, especially for the we are all novices in this topic. So a topic which we have to learn again. So I thought.
Do you want me to send it to the Tamil Nadu Academy Neurology members also?
Please do it.
Okay, because I have to take your concurrence. So
no, it's all right.
Do it immediately. Yeah,
give it, no problem. It's it will be available on YouTube also.
Yeah.
So if you agree, then I'll start at 8.
Yeah, I think you have.
It will keep coming.
My radiologist had also
interested.
Agreed to join. Would you like them to join? Then I'll give a call.
Yeah, please give them anywhere, whoever wants.
We'll wait 5 minutes, sir. We'll just wait 5 minutes.
Okay.
Dr. Subhadra, we are starting. Okay. You have the link, no? You have the link. Yeah. Yeah. Okay.
Yeah.
People have not joined the meeting.
They are joining.
No, I'm talking to my MSc.
Yeah, okay.
Why I have sent the link and everything. So yeah, just remind everybody, including the first years.
So, Sunil, I think we should start.
Yeah, I think we'll start.
Yeah. Good evening, everybody. Today, I'll be talking of a topic which is of very great importance. That is the application of artificial intelligence in in general medicine, in particular neurology, especially in prognostication of acute ischemic stroke. So, before we touch the topic, as you know, when we were in MBBS and MDDM, we were not taught research methodology, critical appraisal skills. We have learned them slowly. And we are faced with one more challenge now. We have to learn about artificial intelligence and machine learning. Very important for all of us. So I'll address this in introduction to stroke and AI. Before that, I'll talk about what is artificial intelligence and a bit of machine learning. What do we understand about it? Mind you, I am not a programmer, but I have worked with data scientists so that I gain some knowledge, and it's a self-taught one by doing some courses. And we tried building up an AI model, and there are methods to evaluate these models. And the development of a model to prognosticate a stroke is our main research work, where 3 PhD students and they have worked with me. And then I'll show you the stroke and AI study. Suppose if you are standing in a railway station and suddenly you come across a friend, you recognize the face in a crowded environment. It's a routine task to us, and we don't know how we did it. It's not because of he got brown eyes and some sharp nose, because billions of people have same features, but there's something which is there which we make us recognize that. Similarly, sounds also recognized. But for computers, this task should be broken down into many little tasks covering the minutest of details. That is very tough for computers, but they do help. These tasks, small tasks, are called artificial intelligence. In fact, there is no correct definition of artificial intelligence, but artificial intelligence works through machine learning, which is a type of computing technique that solves a lot of AI related issues, which you can say. What is artificial intelligence? It's a problem solving technique that uses a computing technique called machine learning. That learning is from a known data set to formulate rules and makes predictions from an unseen, unlabeled data set. So Mr. Turing was one of the original inventors of the computer also. He's responsible for breaking the Nazi codes in World War II. He invented the basic ideas of artificial intelligence. In our day-to-day world, we see its applications in a variety of subfields, and they are incredibly useful things. And computer vision, when computers that can see and understand; the natural language processing, computers that understand human language; the Google search engine, which is based on sophisticated natural language processing; robotics, and even computational creativity, robotics that can run factories, computers that can make creative works of arts. They can even diagnose diseases from looking at images. So these are all task-specific intelligence. They are called task-specific intelligence. This is in comparison to human intelligence, which is called general intelligence. So far, computers have not entered into general intelligence. They are to be trained task specifically only. So how do we get the computers to understand images, to recognize tumors, tell the difference between good collaterals, cerebral collaterals, and poor collaterals? We ourselves do not exactly know how we recognize a face. So how can we expect computers to be programmed? So computers need not be programmed, for example, for this art. The machine learning is a new technique. Here, instead of programming a computer by telling it every detail of how to do a task, we teach it by giving examples of what to do. Computers learn from the data. So neural networks, which were established in 1940s, way back in 1940s, neural networks were it, but they were not in vogue because we didn't have data at that time. Now at present we have a lot of data available, so these things are coming into vogue. So what is machine learning? It is about creating statistical programs called models. A model takes an input and gives you back an output. The input could be an image of CT angiogram, and the output could be the good or bad collaterals. The model is created based on lots of example data. Each example includes both an input and an output. This is a basic essence. So a machine learning algorithm takes the examples like many images of CT angiograms whose patients we have seen. These are retrospective data. We know how they fared. We know their clinical characteristics. We know how we treated them and how they have improved or they have deteriorated. We know their outcome. We know, and we use them as an examples to train the model. It maps the inputs in the example data to the corresponding outputs. Now, for example, we want to see images of cerebral collaterals on a CTA, and because we have data on how they have improved, we know that there's a good outcome, there's a bad outcome. So we can output figures are outputs are these. So once the model has been trained, if you give a new CT angiogram to this model, that is input without a label, whether it is good or bad, it will tell you the output, whether it is good or bad. So that is the importance. Important is anything that's represented on a computer is basically represented as a bunch of numbers. So this a bit of mathematics, though I'm not going to elaborate on this, but just give you a flavor of this. The most fundamental unit of a digital information is called a bit. A bit is something that can only have one or two states at any one time. That is 1 or 0, on or off, black or white, true, false, yes, no, high voltage, low voltage, right, wrong. That is binary outcomes. So a bit is an abstract representation that can represent any duality, any binary distinction between two things. Computer memory is typically measured in gigabytes. A byte is 8 bits, and a gigabyte is a billion bytes. So that's 8 followed by 9 zeros. That's it. Modern hard disks can be measured in terabytes, and which would be 8 trillion bytes. So by combining a lot of bits together, you can make numbers, letters, sounds, pictures, videos, and everything else that you can store in a computer. So memory is always addressed in large chunks. One very commonly used chunk of memory is a byte. A byte is 8 bits. It's the standard measure of memory. A bit as a 1 or 0 can be stated, and a byte can represent many bits. So these are bit patterns. 256 different patterns of ones and zeros are available. They're called bit patterns. Each pattern can represent something different. For example, letter A is represented by 0, 1 and 5 zeros and 1. Similarly, images are stored as pixels. The picture element, 1 byte is equal to 8 bytes, and number of bytes vary for pixel. So with this basic information, we'll discuss what are the limitations. Like we used to say, for computers, garbage in, garbage out. Same thing applies to machine learning also. But no doubt it's a very powerful technology, and it should be used in a correct way. But there will be bias in machine learning models. This is because the real world itself is biased. So a lot of data from real world is biased. When such a data is used, the ML algorithm develops what is called algorithmic bias. So we should be careful about the data sets we use, and the data sets are to be representative. What features are included are very important. Potentially biased ML systems are weapons of math destruction, is called by scientists. For example, one company may come to you and say that you please use this model, and it will give you the measurements of the brain. It will give you hippocampal volume, maybe midbrain volume, it will give total volume. But you should ask, how did you develop this model? What are the input data into this? Where did you develop this model? Is it across India? Is it only in one state? And what are the numbers you have used? So these are the questions. Unless we know the background, we will not ask, and we'll coolly accept the model which may prove to be useful or which may not prove to be useful. So with this introduction, we'll go into the stroke and the AI. Why the artificial intelligence is especially useful in stroke is the treatments of stroke are all time sensitive. You know, there's a no doubt it's a major health problem, but all the treatments are highly time sensitive and decisions are to be done very quickly with high accuracy. So AI is ideal for stroke treatment, and this figure we all know. And next is right. Another important aspect is stroke treatments are to be provided in remote areas where expertise is unavailable. Then this application is very, very useful. So in future, we'll be seeing more of these applications which are useful to us. So why it is ideal for stroke? Stroke is a common disease and a large databases are available with each institute. What you require to develop a model is database. Clinical characteristics can be quantified very well. The presentations, the NIH stroke scale, the functional outcome, the clot burden, and the infarct volume, etc., are already there are images available, and we can easily tap them. New algorithms can be implemented into patient care pathway very quickly if we apply our knowledge. So, what is machine learning in detail? Arthur Samuel in 1959 defined machine learning as a field of study that gives computers the ability to learn without being explicitly programmed. We don't have to program them, but they learn. I'll show you how they learn. Neurology is the forefront in adopting this technology, and more and more number of papers are dealing with this. This technology in the field of neurology is moving very quickly. Very soon is going to change the clinical practice. In fact, AI has revolutionized the research in neurology. In the last 20 years, more and more imaging algorithms are becoming popular. You can see the number increasing, and FDI cleared algorithms are also available in the public domain for usage and develop models. So the algorithm development typically starts with untrained data set. That means you should go through all the medical records which are available with you over last 300, 400, 500. And to a prior FDA approved algorithm, the data is fed so that important internal parameters are captured for future prediction. There are various types of algorithms in existence. Supervised learning, where labeled output data sets are used, is commonly used. So for stroke, we require a data set which has got the presentation, the neuroimaging, the output also with us. Because the only major limitation is manual labeling of the data. You can see the model attempts to learn the appropriate internal parameters that allow it to perform the task. And so this is how the model works, the training model, which will show in the real life how it works. Also, the inference, the output is here. The model parameters are fixed. Model can produce the required output on data unseen during the training period. So once you train the model can be used to predict what is unseen data set also can be used, and you can predict the answer. So machine learning, there are two ways: supervised learning, which develops predictive model based on both input and output data. That is what we got stroke cases who have been diagnosed. Now we see the outcome. This can be classification or regression model, which is called unsupervised learning. This is a clustering. Here output is not known. A group and interpret data based only on input data. This is a type of machine learning. Then we usually use supervised learning. So the labeling data, this ML methodology, you can see the edema, which is in the dark color, enhancing tumor code, that is in the white color, necrotic and non-enhancing tumors. And you can see the whole model is this example of 4 different MRI modalities and a ground truth labels of a high-grade glioma in data set. So similar tumor models, data sets are collected and fed into the algorithm. That is an image classifier, which I'll show you. So, and what it does is it captures features. The whole thing is not to be learned. There are certain features. It captures the data sets, the data is retrieved, data processing and wrangling, and all these things again I will discuss. The important point to note is feature engineering. The features are captured in the machine learning, and we'll talk about deep learning also, where neural networks will come into play and which will give us the output. So deep learning is a type of machine learning with artificial neural networks. Here there is less human input, but large data requirements, large MRI images, numbers 800, 1000, 2000, 3000, more computational power it has. It extracts the features and the model is classification within the model. The compact data is learned in deep convolutional layers, and higher layers help in final algorithm definition. So that means there are 2 or 3 or 4 layers, which you can see in the next diagram. So this is the input image, which is being fed. Lot of these images are fed convolutional layer. That's how once they are fed into this, and the pooling layer and artificial neural network develop, and here the output. So all the data enters here and output comes here. So this is the deep learning. And what are the steps in building of a model? It's very interesting to learn this. What is the data we require for building a model? Clinical characteristics, NIHS, stroke volume, cerebral collaterals, clot burden. The step 1 is the DICOM images, which are to be converted into digital image. The original image has a lot of stuff that is not wanted and can mess up with the final analysis, hence masking and clipping is applied to remove this unwanted stuff. So images are resampled so that they all are having same features across the data sets. Finally, the region of interest is isolated by a process known as field of view detection, wherein various soft tissues, including nasopharynx, are stripped. I'll show you. So image data conversion, voxel normalization, image resampling, field of view detection, skull stripping, and registration. So these are steps in the pre-processing before we start the model. So the original image you can see here, and we are masking and stripping things which are not required. For example, this thing is removed here. Now we remove that, and final image is like this. And also you can see the unwanted soft tissues like nasopharynx, the skin, the skull, these are removed, and only the field of interest is isolated here. So this is the second step of pre-processing. Field of view detection and skull stripping is done in the method. So upload all the images into a common space. Here in this common space, where and how the images are acquired is immaterial, but all the images, they look alike there. And so now the first task is registration. What do you mean by registration? Is that it is aligning, transforming, and changing images so that different modalities of images from different patients acquired with different techniques at different times could be put together and compared. So we do registration of MRI, CT, angiography images. And you can see this is the registration part of the task which we are doing. And task 2 is classification. The images are fed into an algorithm which is FDA approved, which must see whether the image fits into A, B, or C, which you have classified. For example, A classification is good collaterals, B is poor collateral, C and mixed. So then the training of a data set starts. So so a lot of images are fed into this algorithm, which I'll show you the image classifier in coming slides. The first is registration, second is classification, third is detection. The major application of AI in ischemic stroke is detection of large vessel occlusion. We all know there are scales at the emergency level to find out whether a large vessel is occluded. The NIHS stroke scale, if it's more than 8 or 12, is short. There is a VAN scale where vision, aphasia, and neglect will tell us. But the ML technologies are first and most widely used real-time decision-making softwares that are available for us. And you see that is a detection of large vessel occlusion is facilitated by this. The segmentation is another one. It's a method by which at a voxel level, a different label is assigned to different regions of the brain. The MRI scan is segmented to widely used regions and color-coded. These color-coded images are fed into an algorithm, and one can measure volumes of hippocampal etc. And you can see these are the color coded images which are used in segmentation. How do we know that ML algorithm works? There are many commercially available algorithms. There should be a method to evaluate their performance, and these are called classifiers of precision recall, positive predictive value, or the area under the curve, or the then F1 score. These are things which are the engineers use. These are the receiver operating curve. If one is there, that means the sensitivity and specificity is equal. You can see how it scores. Usually 83 to 87% the algorithms are able to give the output. The segmentation is F1 score, it's a die score. That depends on the overlap of the images. And when you see the image, this is a image that's from the from the solar system, and you can see the ground truth. What we require only the features to capture in this, and you can see the total number of pixels which are combined, which are not combined, or that you can see the F1 score can be developed. So that's a technical part which is not in my purview, but I know that this has to be done. Development of a model to prognosticate outcome in stroke. What do we do in this model? See, our work started way back in almost 2018 when we published this paper, Prognostication of Ischemic Stroke based on stroke volume. And we assessed the volume by using a software called Analyze software, and Vikram is here in Pune in Command Hospital. And then we published, we presented this in American Academy of Neurology also, an observational analytical study of cerebral collaterals on CT angiography in predicting functional outcome in patients with acute ischemic stroke and anterior circulation. So we did a lot of studies on cerebral circulation and CT collaterals, good collaterals and poor collaterals. One of the conferences I asked Dr. Ravi Annadre to come and give a talk also, and that happened in 2018. So in building up of a model, we have a derivation cohort, we have a validation cohort. In the derivation cohort, we got a training data set and a testing data set. So suppose if you have taken 1,000 case records and you got 1,000 images with you, you divide them 70%. I'll use them for training, and remaining 30% I'll use whether the trained model is giving optimum result or not. That's what is something which is done. So good collateral in our set, it's a good collaterals and poor collaterals, because we know the outcome of these patients. These are from our retrospective data. We have fed these are called examples, and we have fed in learning algorithm, and we developed a model so that when an input is given to this model, we can get the output, which will show how we did it. So the derivation cohort, the training data set, good collaterals, we collected a number of them and a number of cases. I mean, usually require in thousands, but we did only about 140, 150 is the only part of it I am presenting here. And the derivation cohort, the training data set also, the poor collaterals and good collaterals you have seen now. What we do is 70 to 30 good collaterals and poor collateral things we segregate and feed into that learning algorithm. So this is the image classifier, and into this, each of these images are fed, and we have already classified into this. Then when we see that, you see the classification, these are from file, you load an image to classify, and you name the classifier. This is the good collaterals, and this you can classify poor collaterals, and you can combine mixed ones, and you put the image into this. It will immediately get loaded here. All the images one after other, you can load them, and you can load the number of images into this. You can see the good collaterals are loaded like this. I've given you 9 examples here. The poor collaterals I've given about 11 examples. Then what do you do? Next time, when you don't unknown image, you load and you see what class it predicts. The predicted class is 6 examples, and it has done correctly. It is classified a good and poor into poor. So this is a very, very interesting thing which you all can do. So the good collaterals are classified when you trained a model, you put an unknown image, it will classify into either good or poor collaterals. So this is an unknown one, which in this model we are putting, and it is given as an output poor collaterals. So that's the magic of the machine learning. So the important applications are to detect large vessel occlusions and identifying candidates for thrombectomy immediately, and identifying candidates for thrombectomy without CT perfusion. Now, in our country, CT perfusion is not done everywhere, but CT angiography is now luckily available in most of the places. So first one is the left, the large vessel occlusion detection. You can see that this type of thing we have to detect, and the area under the curve, as I said, it's very good. So already we can have a good specificity and sensitivity of this. The second one is measurement of the volume. Candidates which are for mechanical thrombectomy, that means diffusion perfusion mismatch, and what is the extent that you can calculate by F1 score, which the scientists will give us. And third one is very important, which is very interesting to me, because I would like to select my candidates for EVT without CT perfusion by only looking at CT angiography and distribution of cerebral collaterals, which is the work in progress. And we are seeing some papers on this where you are getting good sensitivity and specificity of this particular model and detecting infarct volume according to core volume site detection of infarct core. So we are able to achieve some success, and I hope that it will be available in our arena to implement the patient care. So without CTP, the stroke and AI, and this can be used. And I'll show you some examples what we have done in our this thing. So this is a ground truth identification of the output properties. What is our study stroke, and what did we do? So this protocol is published in BMJ Open systematic review protocol to assess artificial intelligence diagnostic accuracy performance in detecting acute ischemic stroke and large vessel occlusions on CT and MR medical imaging. This is by Srinivasa Rao Kundeti, and we all his Phillips colleagues, some engineers. These are the data scientists. And AI model objective is estimation of infarct volume in acute ischemic stroke. And second one is to predict dichotomized 7-day MRS, 0 to 1, more than 2, depending on the clot burden score and cerebral collateral score. These are two things which are very important. These are the images which gone into the. So 48 acute ischemic stroke patients were used for stroke lesion segmentation. The outcome is defined MRS less than 2 is good outcome, more than 2 is poor outcome, and various clinical characteristics are they helped us in classification of this data set. So the lesion count, lesion volume, lesion localization in lobes, all were taken into consideration. And the machine learning model correctly classified all patients with accuracy of 83% with F1 score of 80% as a good outcome and poor outcome. That means we are with growth rates, if you add, then that will give more when how the infarct is growing. We are able to label that and show it will give better results. The study population characteristics of the CT angiography, that is CT cerebral collaterals and clot burden, about 42 patients data we are showing here. The mean age is 64 years plus minus 15. NIH is 16, aspect is 8. And similarly, we have taken all the baseline clinical parameters to define the data sets into good outcome and bad outcome, and we have tabulated all the risk factors. And neuroimaging scores on CTA, we have used the modified TAN score and MAS score to classify the cerebral collaterals. The regional leptomeningeal score is also used. You can see these things are helpful, and which score is helpful for us in saying that he will have a good outcome or a bad outcome, which I have already shown when we presented in American Academy. So simple CTA image annotations, and you can see that how these annotations are done by the data scientists. Then you can see them. The annotation for clot burden score, right MCA M1 occlusion and right MCA M2 rare occlusion. You can see the M1 occlusion, the rare occlusion. You can see this M1 occlusion. So these are the annotated images. which the data scientists work on this, and they label the ground truth in the CTA and MRI images of the acute ischemic patients. The clot burden and collateral score labels are given. Here is a 66-year-old man who presented with difficulty in walking and swaying. So there is the MRI revealed an acute infarct in the right corona radiator, right lentiform nucleus. CT angiography revealed right ICL long segment thrombosis and proximal M1 MCA thrombosis, resulting in a clot burden score of 5. The collateral score on the mass grading scale was given, and the 3 months MRI score was 3, which is poor. So the grading scale, the mass gave us the idea that it's so all these put into together. Like that, we have many cases where we have the 4 cases I'm showing here, where the CT angiography and MRI images are used to the CTA revealed left distal M1 in this and inferior M2 segment thrombosis. And here the MRS score was 1 because the mass grading scale was only 3 and clot burden is 7 in this case. So he has got a good outcome. We can label that as a good outcome. Similarly, third case, the MRS score was here, outcome was 1 because the clot burden score is 7 here and the mass grading scale was 4. So these are the inputs that have gone, and we have labeled the output as good or bad outcome depending on the MRS score. And similarly, the fourth case, the collateral score on mass grading scale was 2 and the 3 months MRS score was 6 because he didn't survive. There is a clot burden score of 3, but he's a large infarct and he died. So the retrospective example data, the clinical parameters, the NIHs and the neuroimaging scores, that means the cerebral collaterals and clot burden, are used as training and testing data set to predict dichotomized functional outcome at 7 days. That is poor outcome as or good outcome. So what are the clinical parameters? Clinical scoring, neuroimaging scores, and these are the various machine learning model ensembles. All the 3 models are used. There are support vector machines, artificial neural networks, random forest model in this case. And you can see ensemble of machine learning models is built to extract diverse features from the data. So you can see that there are the three models used. And ML models ensemble of ML algorithm. What did these 3 models, SVM, RF, and NN, that demonstrated that neuroimaging cerebral collateral scores of all the 3 prognosticated 7-day post-stroke MRS with an accuracy of 84.75% without clinical scores and parameters. So the machine learning model ensemble based on objective imaging criteria of clot burden score and cerebral collaterals yielded a robust prognostication model in acute ischemic subjects with large vessel occlusion than subjective scores that are based on clinical parameters and NIHs. So this is a table which is seen in the 42 patients, the AI model and the clot burden, collateral score, the baseline characteristics, clot and collateral scores together. You can see without clinical parameters, with clinical parameters, the results are shown here, and this is the result. So this paper we now presented in American Academy of Neurology this year, application of machine learning models to prognosticate functional outcome in patients with acute ischemic stroke secondary to proximal large vessel occlusion. So conclusion and the future directions. AI models, they improve diagnostic precision. They assist patient selection for various therapies. Various therapeutic options can be suggested. The most important thing is a team approach of neurologists, neuroradiologists, and data scientists. They should work together to build an effective ML. And the team which I have is Madam Prakashini, who is the HOD Radiology, Kasturba Medical College. The scholars, Srinivas K, the data scientist, scholar Kritishri, the basic sciences postgraduate, and Priyanka Sridhan is a basic sciences graduate. So these are all the team who have worked on this, are still working. And one way I'll finish by saying that all models are wrong, but some are useful. Just remember what I said. The ML models dependent on what data you are using. If data is biased, the model is biased and you'll get wrong results. So, but whenever somebody comes and tells you that this is going to measure this is going to do this, you question, how did you develop this model? Now we should have some background knowledge to judge the sensitivity and specificity and to ask these ROC curve analysis and F1 scores. That's all from my side. Thank you very much for your patient hearing. I'm open for any questions.
Thank you, Professor Gothi. I'm sure that you all enjoyed this talk, even though we have not fully understood it. I'm sure that all of you got a good idea about the concepts, and I think it's absolutely important that we all embrace artificial intelligence applications, because if not today, tomorrow you're going to do it, just like learning new apps in the mobile phone and in every other walk of your life. So medicine is going to be, and this is not going to certainly threaten our careers or anything of that. It's only going to make our works easier. We can check ourselves. We need to utilize this maximum. So I'm sure that this will be a very welcome development. So, Dr. Gothi, we have some questions. Can I?
Yeah.
Yeah. Dr. Subhadra is our associate professor in JIPMER, and she is asking a question. Which software was used for skull stripping, etc., in the pre-processing part?
See, I told you, no, this is by my data scientist, Dr. Srinivas. I can ask him and tell. Because right. We provide the clinical characteristics and follow-up, and he does the. So why my idea for taking up this topic is that to sensitize all the people that we should learn about it, we should know the basics. And I myself do a number of Coursera courses to learn it. So there are a number of courses available. So all the younger generation, my request is that they should do the courses and get a flavor of what we are dealing with, because people will give us models. People will give us, tell us, use them and give them answers. So before we use them, we should know what we are using.
Dr. Gothi,
I can get back that details, what was used by Srinivas.
Right, okay. So I have a basic question. At some stage of your talk, you are telling that usually you need, they are best designed for big data. You need huge amounts of patients or participants to generate this data. But also down the line, I also saw that you had developed some models just based on data from 8-9 patients. And then you said that
no, that's what I showed how to do it. It's not about this thing. I wanted to do, that's a part how you develop a model. I just wanted to show. Okay. But whereas our data, which is about 150, 170, and it's going on, that is separate. What I showed is the image classifier is how to do it for the younger generation, that you can do it. You can learn this technique. You can upload the images. You can convert the DICOM images into a digital image, upload it, and classify it. That's what I was trying. It's not the data is only for example, not the real paper.
Right. Okay. So I think since medicine is a very complex science and there are lots of covariates which determine the outcome, I think the models will continue to be refined more and more as new interesting players come into the field, like other variables which can.
Sir, only nowadays rapid software is being used to detect the stroke volume, and which is about 16 lakhs the installation charges, and it costs about 5 lakhs per year, I think, their rent. So that's what is available from outside. It's very costly, and that's why the indigenous methods are being developed to develop these models. The important thing is we have to learn and we have to work with data scientists.
Right. Yeah, I know. I was, when I say new players, I was not talking about new apps or anything. I was talking about, suppose you have now, suppose you are developing a model on outcome prediction based upon the imaging and risk factors, collaterals, etc. There will always be scope for several other stroke-related variables also to be introduced into the model, and you can keep on refining this, isn't it?
That's correct, sir. The new algorithms can be created and were put into use very fast. Provided we all should, like the institutes have got large databases, and it is the right place for the things to develop. So already I think Sri Chitra we approached, but we didn't take it forward, and they have large database, and some of their data centers also working on this. Like that, you also have a large database, and we can start working on it. We are going to start in other. All Indian Institute has got a large database of neuro. So when data is required for creating models, that's what it is. We should have the output, input data, and outcome also. What happened to that stroke? Then we can develop. We can train a model and use it with effectively.
Yeah, I completely agree with you, because we do keep getting this kind of collaboration calls from some of the US universities and some pure engineers telling that we have developed it. And most of the time when I ask them, they have had data of some 25 patients or 30 patients like that.
Yes.
And they immediately want to take it to the field for this one. So they
want to test it.
Yeah, they want to probably test it, and then yes.
Because I when I gave a talk in, I know that even I tried going very slow in this talk also, but still it is a Greek and Latin to most of the people because it looks confusing. I tried going slow, but maybe I think we'll have more attempts to interact in this fashion in a more number of studies. One thing important is all have to learn it. It should be self-taught. They have to show interest in this, and they start learning about it by themselves. That's the most important thing.
Right? So, do you are you part of any of these teaching programs which are being organized? Who organizes it? Usually, is it the AI, the engineering science departments?
No, sir. Whereas universities are organizing in Coursera, Stanford University and Oxford University, they organize the machine learning courses are there. They're about 12 weeks and 8 weeks courses, 4 weeks courses, small courses, so that you can get a flavor of what is machine learning, what is artificial intelligence, how it is applied in the medicine, and you can spend a bit of money. And in COVID time, it was free.
I think probably our health ministry should consider introducing this as part of medical curriculum also.
Yes. These courses.
If not today, tomorrow, it's going to come next. One small out of the way question. You said this a bit is easier to understand. You said it has got its dichotomous, either plus or minus, white or black. But when you said about byte, you said 8 bits constitute a byte. So why? What is the science behind this number?
So the memory in computer is stored as numbers only. A is indicated by 8 numbers.
Yeah, that 8. Is there any science by why it is 8?
No, there is nothing like a science in this. It's a mathematical calculation, the statistical algorithm that they developed. And so most of the things, wherever you can say right or wrong, yes, no, the binary duality can be represented in computer.
It's like a decimal system, it's a binary system.
Yeah, it's a binary system, yes, no. In classification also, we get good and bad collaterals. That is a classification type of supervised learning, and where you put in various images and you classify them into good or bad, because we developed a model, and that model will tell us that yes, this patient has a poor collaterals and is likely to have bad prognosis.
Right. Usually our Dr. Partha is there. He used to be very active. I'm sure you would have been delighted to.
No, I don't know. I think he's not there.
I think he's probably having some vacation or something.
Yeah.
Otherwise,
he's usually, but I think only younger generation are there. But I think we had good interactions, and maybe some people will see it on YouTube and come back. But I'll certainly come back.
Any more questions? Yeah, I think Dr.
It was
Subhra is
a
taking
very
note.
interesting talk. Thank you very much.
0 is low voltage, 1 is high voltage. Oh, okay. So, right then. So,
Shall we
thank you
say
for
good night, sir?
nice initiative and leadership in this category. We will, I'm sure we'll have more interactions in this specific field also, because there is already some work with IIT we have been planning, but I think probably you are as good a resource person as the IIT people, or maybe even better. So, or maybe it could be a combined work. So I'll get back to you on that. Anybody else has any burning questions? Otherwise, we will close the meeting today. And
Wonderful presentation, sir. I enjoyed it a lot.
Thank you.
I had many questions, but I will go through I want your slides. Can I get your slides at my email?
They are available on YouTube. You can now, I put it on YouTube. Neuro E-Part Seller. Subscribe to that and it will be there.
Okay, okay.
It's
Thank
a free
you, sir.
subscription.
Okay, okay, sir. Thank you, sir.
I just want to remind everyone that our next stroke journal club will be coming, it's in the month of May. So May 7th it will be, no?
Yes, sir.
Yeah. So it's again going to be another interesting paper from Sri Chitra Tirunal Institute. So please join, and we would want you to read this paper in advance and be quite familiar with that. Go through it critically, and please come back with your comments, and so that we can have good discussions. And we'll all learn how better to analyze and read between the lines. Thank you, and
Thank you, sir. Thank
good
you.
night, and
good night, sir. Good night.
Have a nice weekend.
Good night.
Good night, sir. Good night.
Good night, everyone.
Bye, Dr. Goti.